Welcome to section 16.7. In this section, we are going to be talking about the concept of surface integrals. So we saw in the previous section the idea of parametric surfaces, surfaces that can be written in terms of two parameters, u and v. We're going to be then extending this idea. So just like we had parametric curves that allowed us to take line integrals over those curves, we have now parametric surfaces that allow us to take surface integrals over them. So suppose we have a surface S with a vector equation R of uv given here, with u and v in the domain D. The surface integral of f over S, so it looks like the double integral symbol, so this is a surface integral over S of f of xy at z ds is equal to the double integral over D of f of r of u and v times the magnitude of ru cross rv dA. So we see that the function f is being evaluated in terms of u and v, right? All of the x's, y's, and z's are getting replaced by their uv counterparts, and we need to find those tangent vectors, cross them, and find the magnitude. If you compare this to the line integral formula that we developed a few sections ago, that formula was the single integral from a to b of f of r of t times the magnitude of r prime of t dt. So you can see pretty similar in their general form, right? We're just translating everything up for an extra variable, okay, moving from curves up to surfaces. Notice, if we were to take the surface integral of 1, this is, as it often is with an integral of 1, a special case. We end up getting the function becomes 1, so all that's left is the magnitude of ru cross rv dA. And that, which is something that we had talked about in the previous section, that is area of the surface S. So that is surface area. Okay, so if the function in the integrand that we're integrating is 1, then this surface integral gives us surface area. So let's take a look at an example of computing a surface integral. So compute the surface integral over S of x squared ds, where S is the unit sphere. So we know how to parameterize a sphere, and we know that the radius of this sphere is 1, so that's the rho value is 1. So we're going to set up, so x, it would be rho sine phi cosine theta, but we know that rho is 1, so we'll just leave that as a 1. So this is just going to be sine phi cosine theta. Y, the rho is 1, sine phi sine theta. And z is rho cosine phi, so that's just 1 times cosine phi. And our standard bounds on phi and theta. Phi goes from 0 to pi. Theta goes from 0 to 2 pi. So we can create the vector equation. So r of phi and theta. Okay, so that's going to be xi, yj, and zk. So we're going to have sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. So this would be our vector form. for those components. Now, in order to set up the surface integral, we would need to find the magnitude of our phi cross our theta. Luckily, we have already worked with this unit sphere before in a previous section. So we'll just note, so we previously found that the magnitude of r phi cross r theta is just sine of phi. So we're going to be able to use that. So our surface integral over s of x squared ds, that's going to be the double integral over d of x squared, so that's going to be sine phi cosine theta squared times the magnitude of r phi cross r theta, so that's going to be just sine of phi dA. And in this case, phi and theta are the variables, so we'll set up, so let's see, that's going to be sine squared phi, and there's another one there, so that's sine cubed phi cosine squared theta d phi d theta, with phi going from 0 to pi and theta going from 0 to 2 pi. So now we have this double integral in two variables. This one actually can split because it's got constant bounds and it's got a product of a function of phi times a function of theta. But that'll be left as an exercise if you want to try that one out on your own. But we should get out 4 pi over 3 for this one. Okay, so we parameterize the surface, compute that necessary magnitude of the cross product of the tangent vectors, and then solve the integral accordingly. Now, we've seen in previous sections that when a surface can be written using a function, when we have a surface that can be described with a functional relationship, so down here we have the equation z equals g of xy, where x is x, y is y, and z is a function of both x and y. The formula actually can adjust itself to help save us some time. So this would become, the surface integral is the double integral over d of f of x, y, g of xy, times, instead of that generic magnitude formula, this is going to be the square root of partial derivative of z, get my order mixed up here, 1 plus, order doesn't really matter, plus partial z respect to x squared, plus partial z respect to y squared, dA. Okay, so we've seen different versions of this formula before, including in our surface area work from just the previous section. Okay, so we said that if we know that the function can be parameterized using a formula such as, f of xy, g of xy, something like that, we don't have to go through all of the work of finding the tangent vectors, crossing them, and finding their magnitude. We can just jump straight to here. So, case in point is an example at the top of the next page. So evaluate this surface integral of y, where s is the surface, z equals x plus y squared, with x going from 0 to 1 and y going from 0 to 2. So if we get the partials here, partial z with respect to x is 1, partial z with respect to y is 2y. So we're going to get, surface integral over s equals double integral of y times the square root of 1 plus partial with respect to x squared, so that's still 1, plus partial with respect to y squared, so that's 4y squared dA. So we have double integral of y times 2 plus 4y squared. And then all the bounds are constant, so it doesn't really matter the order of integration. So we'll do dy dx. So y goes 0 to 2, x goes 0 to 1. And actually, you can even split this up because there are no x's in here at all. You could just pull x out. Get 0 to 1 dx times integral 0 to 2 of y times the square root. This one just becomes 1. So we get to here. Oops. Which will require the use of u substitution. But if you go through that process, we end up getting 13 rad 2 over 3. So having the surface described using a functional relationship allows us to cut through part of that process and solve it a little bit more efficiently. Now, if we have a surface that is not just defined using one formula, if we have a surface that is piecewise smooth, so this is one where multiple different pieces have come together to form the surface, evaluating the surface integral is just as simple as evaluating the surface integral over each individual piece. So the surface integral over S1, etc., all the way through S sub n. So with piecewise smooth surfaces, you're basically just evaluating multiple surfaces and then just adding the results together. So we're going to take a look at an example of this. So evaluate surface integral over S of z, where S is the surface whose sides S1 are given by the cylinder x squared plus y squared equals 1, whose bottom S2 is the disk x squared plus y squared less than or equal to 1 in the plane z equals 0, and whose top S3 is the part of the plane z equals 1 plus x that lies above S2. So try to color coordinate here. So this surface that goes around the edge, that's S1. That's the cylinder, x squared plus y squared equals 1. S2, I know it's kind of hard to see here, but it kind of is that circular disc down under the bottom. That's S2. So that's this one. And then the top, of course, the one in green right there, that's S3. So that's on the plane z equals 1 plus x that lies above S2. So it's bounded within that circular disk. So if we want to evaluate the surface integral over this whole surface, we're going to need to evaluate it over the individual pieces separately and then add the results together at the end. So we're going to start with S1. And we are on a cylinder, right? This is a cylindrical equation, so we're going to use cylindrical coordinates. We know that the radius is 1, so r will be 1, it'll be constant, but we have then theta and z as our remaining variables. So we're going to use theta, and z. So we're going to get x would normally be r cosine theta, but r is 1, so it's just cosine theta. Y is sine theta, and z is itself, where theta goes from 0 to 2 pi, because we're going all the way around the cylinder. And z goes from 0. So you can see the part of the cylinder we're on here. It starts at 0 down in the xy plane, and it goes up until it hits this top surface, which is this plane, the one that's in green. So it's going to stop once it hits the plane 1 plus x. But the issue is, if everything has to be put in terms of theta and z, we need to go ahead and convert x, which is fine. We'll just put it in terms of theta. That's cosine theta. So that's 1 plus cosine theta. So z is between 0 and 1 plus cosine theta. Then we would need to get the tangent vectors. So we would get r theta, which would be negative sine theta, cosine theta, and 0, and rz, which is 0, 0, 1. And then we would need to cross them together, which ends up producing cosine theta, comma, sine theta, comma, 0. And then we need to get the magnitude of that. And obviously, if we go through the magnitude calculation, we end up getting sine squared plus cosine squared is 1. Square root of that is 1, so that's just a 1. So that's nice. That's going to work out in our favor here. So our surface integral over S1 of z ds, that's going to be double integral over d of z, which luckily is one of our parameters here, so we don't have to change that, times that magnitude, which was just 1. So that's very nice. So we just get double integral of z dz d theta. Z goes from 0 to 1 plus cosine theta. Theta goes from 0 to 2 pi. So we would evaluate the dz. That'll give us a formula in terms of theta, and then evaluate that integral with respect to theta. We end up getting 3 pi over 2, which of course is not the final answer. But that is the value of the surface integral over S1. So with all these, piecewise surfaces, again, it's not asking us to do anything that different. It's just asking us to do more of that same idea. So we move on to S2. S2 is going to be a little bit easier if we just recognize something kind of interesting about it. So we're going to start S2 right here. So notice, so we're in a circular disk in the plane z equals 0. So we're thinking about maybe, using like polar coordinates, parameterizing in that way. But an interesting thing happens here because of the integrand and where this plane is. So we can say, since S2 lies in the plane z equals 0, surface integral over S2 of z ds, as long as we are in S2, this value of z will always be 0. So this will be the double integral. It'll end up being the surface integral of 0, which will just give us 0. So that's very nice. And if you were attempting to solve it in some other way or parameterize in some other way, you would still get the same result, because ultimately, one way or another, the z value will always be 0 there. And then for the plane. So the plane for S3, the plane has a formula that's written as a function. Z is a function of x and y. There is no y listed here, but that's okay. The variable doesn't have to appear to still be a valid variable. So for S3, we're going to take g of xy to be 1 plus x. So our surface integral over S3 of z ds equals double integral over d of 1 plus x. Okay, so because I subbed out z for that formula, 1 plus x, times the square root of 1 plus partial of this with respect to x squared, so that's just 1, and then plus partial of this with respect to y, which is 0, squared is 0, dA. And we're evaluating this over a circular disk. So, in fact, it's that same circular disk from the previous part, okay, of outermost radius 1. So we can go ahead and convert this into polar. So let's see. We're going to have a rad 2 in here. The x is going to convert, so that's 1 plus r cosine theta times rad 2. And since we're doing a conversion from Cartesian into polar, we do need to include the r dr d theta, with r going from 0 to 1 and theta going from 0 to 2 pi. And then this is a pretty standard double integral in polar coordinates, so I'll just tell you what this gives us. So we end up with 3/2 plus rad 2 all times pi. Oh, sorry. No, we don't. I got my lines mixed up. This one is just pi times rad 2. So the rad 2 can come out to the front, and then the rest of the double integral just ends up giving you pi. So got a little bit ahead of myself here. So because now, if we want to find the value of the surface integral over the entire surface, all 3 pieces of this piecewise surface, do that right here, surface integral over S of z ds is just the surface integral over S1 plus surface integral over S2 plus surface integral over S3. So that's going to be 3 pi over 2 plus pi times rad 2. And this is where I went ahead and factored out the pi. So we get 3 over 2 plus rad 2 times pi. And that'll give us our final answer. So here we saw kind of 3 different types of solutions for a surface integral. one where it gets parameterized, one where it doesn't require parameterization because of its location and the integrand that we're solving, and then one where it is already set up as a function so that we can just work with x and y as the parameters. So the next thing we need to talk about in this section are the concept of oriented surfaces. So to define surface integrals of vector fields, we need to rule out non-orientable surfaces. So a non-orientable surface is a surface that does not have distinguishable sides. It doesn't have like a top and a bottom or an inside and an outside. It's typically, we would consider it like a one-sided object. One good example of this, more common example, is the Mobius strip. Mobius strip, a lot of people are pretty familiar with this. If you're not, it is an example of a one-sided object. You can actually create your own, even just using like a slip of paper and like a piece of tape. But I want to just show you really quickly in case you're unfamiliar with a Mobius strip. So, where did this go? Doesn't want to work for me now. Nope, it's not what I wanted. Let's try this again. There it is. Okay, so this is the Mobius strip. You can see here, it appears as though it might have two sides, right? It looks like it has kind of an inside and an outside here. But if we follow the surface, so follow the edge of the surface here, you can see we're kind of on this flat backside right now. Let's follow it around. And you can see it levels off on top. So we go on top like this. And then it kind of banks inside, kind of along that back inside edge there. And we're following it around on the inside. And notice it starts to dive down under down there. So in the back where that twist is, it dips under. So now we're down there on the far side. And we get right back to the backside, which is where we started. And you can do that without ever actually, if you were going to trace this, you could do it without ever lifting up your pen or pencil. So both, what we would consider both sides of this are actually connected and they form one side. So this makes it incredibly difficult to work with calculus because if we're trying to identify things like normal vectors and tangent vectors and such, we need to be able to distinguish a direction that the normal vector should point based on like inside versus outside, top side versus bottom side. But a surface like the Mobius strip does not have that because if you're on any particular point on the Mobius strip, your tangent vector, if it's pointing up, well, who's to say that that point, it shouldn't be pointing down instead? Because it's the same side, right? If I take the tangent vector at any given point, who's to say that it's supposed to point up versus down or inside versus outside? Because all of it is the same side. Okay, it's all one big side. And that's something that, we have to wrap our heads around a little bit. But this is the idea of a non-orientable surface. So basically, I bring all of that up to talk about the fact that we are not going to be working with those in this class. We are going to only consider orientable surfaces. Okay, or, a simpler terminology for that would just be two-sided surfaces. Okay, so surfaces that do have an orientation to them. So for a surface S, there are two unit normal vectors at the points x, y, z. So we have the vector n1, so that's right here, pointed outward away from the origin, and n2, which is the opposite of n1. So notice this one's pointed back in towards the origin. And again, we can distinguish them because of this idea of one vector pointing out, one vector pointing in on this two-sided surface that we have. N provides S with an orientation, and there are two possible orientations. So if S is a smooth orientable surface given in parametric form, it is automatically supplied with the orientation of the unit normal vector. So our unit normal vector, n, that's just going to be RU cross RV over the magnitude of RU cross RV. Okay, so that is, right, the tangent vectors crossed together gives us the normal vector, and then divided by its own length, that gives us a unit normal vector. So that would give us the orientation of the surface, okay, pointed outward like that. The opposite orientation is given by negative n, or opposite of n. Notice that n is going to point the same direction as the position vector. Okay, so the position vector pointing away from the origin, so like if we started a vector here and pointed that way, this vector should be pointed the same way as that, okay? Outward, away from the surface, away from the origin. For a closed surface, so you can see like these spheres right here, for a closed surface, the convention is that the positive orientation is the one for which the normal vectors point outward from E. So all of this sets up our work to be able to solve surface integrals over vector fields, okay? Just like we saw line integrals being evaluated over vector fields. So if F is a continuous vector field defined on an oriented surface S with unit normal vector n, then the surface integral of F over the surface S is given with this. So this is surface integral over S of F dot ds, and yes, these are both bolded. That will be equal to surface integral over S of F dot n ds. So the vector field dotted with the normal vector, that unit normal vector. This integral will also more commonly be referred to in applications of physics and engineering as the flux of F across S. So if you hear that terminology thrown around in any of your physics classes, engineering classes, or you may have already encountered some examples working with flux, this is basically what it's talking about. It's just evaluation of a surface integral over a vector field. If S is given by a vector function, R of uv, so we have our parameterized version of the surface, then this surface integral becomes the double integral over d of F dotted with RU cross RV dA. Okay, so if we have a parametric surface here, we take the vector field dotted with the cross product of RU cross RV, and then that produces some scalar field, right? Some scalar function, which we can then integrate using the double integral. So let's take a look at this. Let's try this out. So find the flux of the vector field across the unit sphere. So anytime it's asking for the flux, it's just asking for the evaluation of the surface integral over the vector field. We're working with the unit sphere here again. So we have already parameterized this. So recall r of phi and theta. That's going to be sine phi cosine theta I plus sine phi sine theta j plus cosine phi k, with phi going from 0 to pi and theta going from 0 to 2 pi. So we've already done that several times over now. So if we're going to evaluate f of r of phi and theta, all this is asking us to do, I feel like the notation maybe makes it look a little more complicated than it actually is. It just means take this formula for x, y, and z and substitute into the appropriate places in f. So instead of x, y, and z, we're putting in the formulas for x, y, and z in terms of whatever the variables are now, in this case, phi and theta. So zi, so z is cosine of phi, so that's cosine of phi I, plus yj, so that's sine phi sine theta j, plus xk, so sine phi cosine theta k. So they basically just swapped x and z in their places in this. And r phi cross r theta. So again, we've been working with this one a lot, but if we find r phi, find r theta, cross them together, we end up with sine squared phi cosine theta I plus sine squared phi sine theta j plus sine phi cosine phi k. And what we really need here is the dot product of these two together. So we need to take f of r of phi and theta, dot it with the cross product here, and that's going to form our integrand in the double integral. So if we take f of r of phi and theta, dotted with r phi cross r theta. So this will no longer be a pair of vectors, because as soon as you dot them together, you're multiplying the corresponding pieces to each other and adding the results up. So we're going to get, for the first two, we get sine squared phi cosine phi cosine theta. For the second one, we get that sine cubed phi sine squared theta. And for the third one, we get sine squared phi cosine theta. But notice that's exactly the same thing as this. So the first and the third components end up being the same. So I'm just going to combine them, just get two of them right there, instead of having to write it out each and every time. So our surface integral over S of f dot ds, this is the double integral over d of f dotted with r phi cross r theta dA equals double integral of this, so 2 sine squared phi cosine theta plus sine cubed phi sine squared theta d phi d theta, with phi going 0 to pi, theta going 0 to 2 pi. The solutions for these, they do break apart. So the way that we would need to solve these, basically you would want to split the double integral into this double integral of this plus the double integral of this. And then you can split those across phi and theta, and like multiply them by each other. So you end up getting like 4 single integrals. One of those is going to turn into a 0, which ends up nullifying about half of this. And then the other ones, you have to use a little bit of trig identity and such to do that. So it's a little bit of an involved process, but again, for these types of problems, I'm more focused on our usage of the proper technique to set up these integrals. And once we get to the process of solving the double integrals, I'm a little less concerned about that at this point in the semester. So we end up getting 4 pi over 3 for that value. So, and of course, you're always welcome to attempt those if you're looking for a little extra practice. But that is what we would get. So we parameterized the surface. We evaluated in the vector field. We got our tangent vectors, crossed them, and then dotted that result with F. And that created our integrand. So all of this was just in service of creating that integrand. And then it's a matter of integrating from there. Now, if we have a case like we have seen before several times, where S, that surface, is given by the graph of a function, so g is a function of x and y become the parameters, and our surface integral becomes the double integral over d of negative p times partial z with respect to x minus q times partial z with respect to y plus r dA. So everything gets put in terms of x and y. Okay. P, Q, and R come from those components. Okay. So the components of the vector field. So like with all of these other formulas, having a surface that is parameterized as a function in terms of x and y cuts out steps in this process. We don't have to do all of that setup if it can be written as a function. So let's take a look at this next example here. Evaluate surface integral over S of this vector field F. So F is the vector field yi plus xj plus zk, and S is the boundary of the solid region E enclosed by the paraboloid z equals 1 minus x squared minus y squared, and the plane z equals 0. So you can see I have that over right here. So E is just the solid within that, but the paraboloid is up here, and then that plane is down there in the bottom. Now, in order for us to find the value of the surface integral, we need to work with this in 2 parts. So, because notice that this surface here, most of it is covered by the paraboloid, but there is a surface on the bottom as well. So we're going to have our surface S1, and then down underneath there, so we're going to have S2 is down here. So these together compose our surface S. So S is piecewise smooth, and S is closed, right? So notice that S is completely closed, right? These are bounded against each other. So S is closed. So use the convention of positive or outward orientation. Okay, so in other words, all of our normal vectors are going to be coming outward, and then same thing down here. Any normal vectors that we have are going to be pointed downward. Okay, so just moving out away from the origin, externally of the surface. Now, S1 being this paraboloid right here, S1 can be written as a function, right? So we have x is x, y is y, z is a function of x and y. We can call it g of xy. That's 1 minus x squared minus y squared. So we can go ahead and get a couple of the pieces that we need here. We're going to need the partials with respect to x and y. So we'll get partial z with respect to x is negative 2x. Partial z with respect to y is negative 2y. So we're going to need those. We also need p, q, and r. Those come from the vector field. So p is y, q is x, and r is z. So those come from right there. So our surface integral over S1 of f dot ds is equal to double integral over d of negative p times partial with respect to x minus q times partial with respect to y plus r. So we're going to get negative y times negative 2x minus x times negative 2y plus z dA. But we don't want z. Actually, maybe I'll just rewrite that right now before we get too deep into this. Because x and y are parameters, right? So everything is in terms of x and y. I don't want this z to be my r. I'm just going to rewrite it using what we know z is from the parameterization. So let's go ahead and just put that right here while we're here. So that's right there. That's dA. So we end up with, this is 2xy, this is 2xy. So we get 4xy plus 1 minus x squared minus y squared dA. Now the region D that we're integrating over is everything bounded within this circular disk, right, of outermost radius 1 on the plane z equals 0. So we need to go ahead and convert this to polar. So that's going to be 4r squared sine theta cosine theta plus 1 minus r squared. That would be the x squared plus y squared. And then r dr d theta. with r from 0 to 1, theta 0 to 2 pi. And again, that gives us another pretty typical double integral in polar. We have to split this up a little bit, do a little bit of work on it. But we can definitely get it done, and that would give us pi over 2. So we get the value of S1, so the surface integral evaluated over the paraboloid portion is pi over 2. But we also need to evaluate over the second surface, S2. That's down in the xy plane. So for S2, notice that because this is oriented downward, so because it's oriented downward, our normal vector for this one, it's pointed straight down, and it would be a unit vector, a length of 1. If it was pointed straight up, the unit vector in that straight up direction, positive z, would be k. But in this case, it would just be negative k. Right? Or, the vector like 0, 0, negative 1, like that. So we actually have an alternative version of the formula that we looked at first that we haven't used yet. We can actually use it here. So this is the surface integral over S2 of f dot ds. That's surface integral over S2 of f dot n ds. So in this case, for this surface, that would be f dotted with negative k ds. If we dot the vector field with negative k, that means the I component will be nothing, right, times 0. The j component will be nothing, times 0. And the k component, we will take that and just multiply it by negative 1. So we just take z times negative 1. So we get surface integral over S2 of negative z ds. But we run into a similar outcome that we saw in a previous example, where because the surface lies entirely in the xy plane, the z value everywhere in there is 0. So we get surface integral of 0, which is 0. So our solution here, our surface integral over S of f dot ds, that's surface integral over S1 plus surface integral over S2. Right? Just evaluate the separate pieces separately. So we get pi over 2 from the first one plus 0 for the second one. So we just get a value of pi over 2 for that surface integral. In our upcoming remaining sections, we are going to be looking at relationships between surface integrals and line integrals, and surface integrals, and actually some triple integrals from our previous chapters. So we still have some really interesting theorems coming up that are going to help us solve more types of problems. But that has been our full introduction into the world of surface integrals.